discuss numericals of chapter number 9. The first numerical: a steel wire of length 4.7 meter and cross sectional area 3 into 10 raised to minus 5 meter square. Okay, stretch is by the same amount as that of copper with the length 3.5 meter and cross sectional area 4 into 10 raised to minus 5 meter square under a given load. So load is same, change in length in both the wires are also same. What is the ratio of Young's modulus of steel and copper? Okay, very easy. First of all, data collection: length of steel wire 4.7, area of steel delta ls, that is change in length of steel, is taken as small l, and force applied on the steel is taken as F. Then length of copper, this is area of copper, delta L is same for both, force applied is also same. Now take the ratio of Young's modulus. Okay, Young's modulus, just we are taking the ratio. First of all, we write the Young modulus for steel: force upon area, change in length upon original length. Okay, force upon area, that is stress upon strain. So just simplify this. So Fs into Ls upon As into delta Ls. Okay, instead of delta Ls we write small l. Okay, similar thing for the copper wire: force into length of copper wire. Okay, area of copper upon into change in length, that is L. Okay, now taking the ratio of both these. Okay, if you take the ratio of this to this, okay, then force will be cancelled out, change in length small l will also be cancelled out. So you will have length of steel upon length of copper, length of steel upon length of copper, and this will go in the numerator: area of copper upon area of steel. So just we have to place the values, okay, which are already given, and you will get the ratio of Young modulus of steel to Young modulus of copper. It is found to be about 1.8. Okay, now numerical number 5. Okay, two wires of diameter 0.25 centimeter, one made of steel, the other made of brass, are loaded as shown in this figure. The unloaded length of steel wire is 1.5 meter and that of the brass is 1 meter. So initial length of both the wires are given. Find the elongation of the steel and the brass wire. It's very easy again. Elongation we have to calculate. This is the figure: 1.5 meter steel wire, and the load which is at the end of steel wire is 4 kg. At the end of this 1 meter brass wire there is a load of 6 kg. Okay, and radii of both the wire. Okay, because here there must be a diameter which is given to us. Okay, here the diameter is 0.25 centimeter, so radius will be 0.25 upon 2, and it is converted into meter by multiplying 10 to the power minus 2. So it is 0.125 into 10 raised to minus 2 meter. For steel wire, change in length Ls can be found. Okay, that is force which is applied to the end of the steel wire, original length of steel wire, area pi r square, but radius of steel, Young modulus of steel, and you can find as F which is applied to the steel wire. Try to understand the figure. The steel wire is here at the top, or we can say initially there is steel wire, so it is experiencing the load of 4 kg as well as 6 kg. So total 10 kg load it is experiencing, so its force at the end will be 10 into 9.8. Okay, so force experienced by the steel wire will be 98 Newton. Just place these values here in this equation. Okay, 98, 1.5 is the length of steel wire, and all these values. Okay, and simplify, then elongation in steel wire you can get. Now for brass wire, if you see, then brass wire is experiencing the load which is only of 6 kg, because on the top 4 kg load is not experienced by this wire. Okay. So load experienced by the brass wire is only of 6 kg. So force at the end of B wire, that is brass wire, is 6 into 9.8 Newton. And again, values are known to you. Okay. Forces force at the end of brass wire is 6 into 9.8. Okay. This value, length of brass wire, is known. Okay. It is 1 meter. Pi r square of brass wire, radius of brass wire, is same as that of steel, and Young modulus of brass. Okay. Then elongation you will get by simplifying this as 1.3 into 10 raised to minus 4 meter. Okay. So both the elongations we got.